All right, go ahead and have your homework out if you would, please. Books open to page 265. Just 3 questions to answer last night. We're going to talk about some of the stuff that we read in the previous homework assignment. It's a little shorter assignment last night. Numbers 18, 19, and 22. And question number 18 says, what are the limits of the audio spectrum? Audrey?
20 hertz to 20,000 hertz.
Good. The limits of the audio spectrum are from 20 hertz to 20,000 hertz. Number 19, define ultrasonic and infrasonic waves. Michael?
Ultrasonic waves are above the audible sound, and infrasonic waves lie below the audible sound.
Okay, specifically, they're what lie above or below audible sound? Kendall, did you have that little detail? Their frequency, there we go. Their frequencies are above those of audible sound or below. So ultrasonic waves, based on what we just said for 18, ultrasonic waves are waves with a frequency over 20,000 hertz. Ultrasonic waves, or infrasonic waves, frequencies below 20 hertz. And number 22, what is the relationship between notes 1 octave apart? I actually mentioned this in an earlier lesson. Kendall, what did you have for 22?
The relationship between notes 1 octave apart is that they will sound harmoniously together.
Well, they will sound harmoniously together. So they kind of sound like the same note, just one higher, one lower. I use this in choir all the time. I'm like, yeah, I'm a bass. I'm not hitting that note. I know some people, like, they hate basses. And so, okay, so rant for a moment here, okay? But, okay, bass clef, something along those lines. I don't exactly remember how it looks. It's been a while, but something like that, okay? Notes that are down here are happy. Notes that are above the staff should never be bass notes. If they're above the lines, those ought to be tenor notes. And yet some fool ends up writing notes like this. Or maybe I guess the line's on the other side. But I'm like, yeah, that looks like a great tenor note, but I ain't hitting that one. I'm going to come down here and hit that one instead. Okay, so an octave, yes, they sound the same. It's just one's lower or higher. But what's the actual mathematical relationship? Audrey, what'd you have for 22?
Notes 1 octave apart have the same pitch.
Roughly, they sound like they have roughly the same pitch. Michael, what'd you have for 22? The relationship between notes 1 octave apart.
In order to rise one note, you have to double the previous note's frequency.
In order to rise 1 octave, you'll double the previous note's frequency. Good. So a doubled frequency is the, or if you're going the other way, it'd be a halved frequency. All right, let's go and review some things we talked about recently. We've talked about sound, and we talked about how sound waves will have a certain frequency, they'll have a certain wavelength, but if the object emitting them is moving, those frequencies or those wavelengths are compressed. What do we call the change in wavelength and frequency? Due to motion of the source or the apparent shift in frequency and wavelength due to motion of the observer. Class?
Doppler effect.
Doppler effect. Good. Michael, what's the equation for the Doppler effect? Audrey?
F sub equals F sub S times V sub air plus V sub O over V sub air minus V sub S.
How do we find this V sub air, the speed of sound in air? Kendall?
It's 331.5 times square root T sub C plus 273 over 270.
There we go, good. And for the record, she did do that without looking at her book. So it's right there below the piano.
Oh.
But she did not look at the book while she was doing it. Let's see, when we said that, again, as the object's speed increases, or as the object's speed increases, or as the observer's speed increases, the frequency the source emits will be compressed to a higher frequency until the object, if it were traveling at or above the speed of sound, class, which we call supersonic speeds or Mach speeds, right? If it travels at that speed, the wavefronts will literally be compressed into each other, which means you can no longer have an ordinary series of compressions or rarefactions. There's just a large displacement of air, and which we call a shock wave, which can actually be seen. You can actually see the weird shock on the plane, and this shock wave is heard by people as a sonic boom. And hence, we don't fly across the continent typically supersonically. That's for out over the water or over the deserts in, Arizona or wherever where there's nobody living. Where they do the nuclear tests and stuff and blew up, just that kind of thing. We said that a wave has strength to it. A wave has power that flows in a certain amount of cross-sectional area. What is that term that refers to the strength of a sound wave? Kendall? What term refers to the strength of a sound wave?
Intensity.
Intensity, good. Strength of sound can be thought of as intensity. And we said intensity is the flow of energy per unit time, per unit area. So what was our first equation to find intensity of a sound wave? Anyone?
P over A.
I think it was P over A, where we remember the power class is measured in watts and area is measured in square meters. So what's the unit for intensity? Watts per meter squared. Now we said that it doesn't take a whole lot of power in a sound wave to hear it. In fact, the lowest sound the human ear can hear, not the lowest pitch, but the lowest intensity sound, we call this the threshold of hearing. What was that intensity? I'm going to remember from yesterday.
20.
That's from your reading, the lowest frequency.
1.0 E-6.
Lower than that.
10.
Lower than that.
12.
1 E negative 12 watts per square meter. So I think we said that was a trillionth of a watt per square meter. It's just barely audible. And then, of course, you could increase intensities until eventually you get to a point where pain can be caused. And what was the threshold of pain? 1 even full watt per square meter. And if you go just a little bit higher, I believe it's about 100 or 1,000 watts per square meter, there's enough energy in the sound wave to actually rupture your eardrums. Damage can occur to your ears. And think about it, right? It's just a thin membrane. It just vibrates back and forth. Like, for instance, if you took a balloon or something and you maybe before you blew it up and you kind of stretched it out a little bit, and you kind of vibrate it. Well, imagine if you tried to vibrate it more than it had ability to vibrate. It could either stretch permanently where it'd be permanently deformed or possibly even ruptured. Usually that doesn't happen, right? Normally it's little kids sticking sharp objects in their ears. Unfortunately, ears do eventually heal, but bad idea to mess with your ears. So intensity of sound. And I said this, that because sound is a three-dimensional wave, as it spreads outward, class, it diminishes. Now, the total intensity of the wave front maintains the same, but because the wave fronts are getting larger every time, then the intensity is more spread out. So sound weakens as it spreads outward from the source. You had an equation that showed the relationship between intensity and distance from the source of the sound. Do you remember that equation? We just used it at the very end of the hour yesterday and then didn't really get to do much more with it. Kendall, do you remember that one? Michael?
I1 squared equals I2 squared.
Good, there we go. So the intensity of the sound and the distance from the source of the sound varies inversely by the square of the distance. So I1R1 squared equals I2R2 squared. That kind of brings us up to speed from what we talked about the last few days. Let's talk now about a gift from God. We don't hear intensities. At least our ear doesn't perceive things that way. Imagine if it did. Imagine if the difference between them. Okay, I'm not going to do it. And trying to reach the threshold of pain, okay? Imagine if your ear could detect 1 trillion times difference between that. How sensitive your ear would have to be to sound. That could be a real problem. But God didn't make your ear to perceive intensity. He designed your ear to perceive something called loudness. You say, that does not sound like a scientific word at all. Well, it doesn't sound very scientific, but it's how we perceive intensity. Loudness is the way the human ear perceives intensity. And important to note that while intensity is, like most things, linear, it just progresses linearly, loudness isn't linear. The human ear doesn't perceive linearly. The human ear perceives logarithmically. logarithmically. Now, you might have heard the term logarithm before when people were trying to scare you about upper level math. We did not get very far into logarithms at all in pre-calculus. I touched just a little bit on it. I'm not sure if you two would remember. Algebra 2, we had bigger fish to fry. I want to spend a little more time on other things. So you haven't actually learned, Kendall, anything about logarithms. And frankly, there's not a lot that logarithms apply to on a regular basis. But I do just want to kind of catch you up on what a logarithm means, just so you understand it. Logarithms basically are used to find exponents. For instance, Kendall, if I said 10 to some power equals 100, Kendall, what power of 10 equals 100? What do I have to do to a 10 to get 100?
You double it, or multiply
By 10, so we call that brain freeze class, square it. You'd square it, right? So apparently x equals 2 because that's the power of 10 that I would need to get 100, right? You can do this with other things besides base 10. For instance, 2 to some power equals 32. Well, what power of 2 equals 32?
Okay.
2 times 2 times 2 times 2 times 2. The fifth power, x would equal 5. Logarithms are used to find exponents, variable exponents, basically, is the major use there in algebra. Well, consider this for just a moment then. We would say, since 10 to the second power equals 100, the logarithm, we just say log, of 100 is 2. It tells you what power of 10 is needed to get this thing. So for instance, if I said, well, what is the log of 100,000? Well, class, looking at the number of zeros, what power of 10 is needed to get 100,000? 5. So apparently then that means the log of 100,000 would be 5. And if on your calculator, by the way, if you were to type in the number 100,000, and you were to hit the log button, type in 100,000 and hit log, it'll give you 5. Because 10 to the 5th equals 100,000. Now, consider this though. You can take logs of other numbers as well. For instance, if I took the log of 98. Well, after all, the log of 100 is 2. Meaning 10 squared equals 100. Well, what power of 10 would equal 98? Well, it wouldn't be an integer anymore, would it? But it'd be something like 1.99 blah, 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 wouldn't it? Right, 10 to the almost 2 power is going to give you something that's almost 100. So at your seats, take the log of 98. And it comes to
1.991.
Hey, that was pretty good. All right, that was just a guess. I was kind of hazarding a guess. 1.991 blah, blah, blah. Okay, so for instance, if I wanted the log of 47,000. Well, remember, 10,000 would be a log of 4, right? 100,000 is a log of 5. This is going to be kind of in between. I'm going to guess it's something around 4.5-ish. What is the log of 47,000?
4.672.
Okay, so a little higher than I was anticipating. Log of 4.672, blah, blah, blah. Okay, so you understand you can take logs of other numbers besides ending in perfect zeros, but it's easiest to represent these with perfect zeros, right? So if I had the log of 1 billion, what would the log of a billion be, class? 9. What would be the log of 1 over 1,000? Well, this is a reciprocal, isn't it? What kind of exponents mean reciprocal? Negative exponents. So not coincidentally, if you take 1,000th or 0.001 and take the log, you're going to get a negative value. Because it would be 10 to the negative third. That would give you 1 over 1,000. Does that make sense? Okay, so consider this for a moment. 1e negative 12. Well, if you were to take the log of 1e negative 12, that would be negative 12. Because e negative 12 means 10 to the negative 12. The log of that would be negative 12. Make sense? So the ear, here's the way the ear progresses. Notice the difference from here to here, from 100 to 100,000. That's 1,000 times difference, isn't it? That would be the way intensity works. You could go 1,000 times more intense. It sounds a little bit more than twice as loud. You go from here to here, and that's just insane, the jump in intensity. It's about 4 times as loud. is the way the human ear perceives it. God made our ears to perceive things logarithmically so as not to sustain damage. They don't have to be overly sensitive. Does that make sense? Do we understand how a logarithm works? Okay, so now that we've kind of established the idea of logarithms then, let's talk about how we measure loudness. Intensity is measured in watts per square meter. Loudness, which we're going to represent with beta, loudness is measured in units called bells or decibels, which we're going to represent dB. Now you notice that bells is capitalized. It's not actually capitalized in the word decibels, but bells is actually named in honor of Alexander Graham Bell, right, who came up with the telephone and transmitting sound or loudness in a sense through wires. So named in his honor, bells or decibels. Now the idea here is a bell is actually the true logarithm. Decibels then takes a bell and breaks it into 10 more parts, and what has been found is you can barely tell the difference between 1 decibel and the next. It's just barely noticeable. The difference between bells is a little bit bigger. So by going to decibels, tenths of bells, we're able to be a little bit more exact in our calculations. How would we convert this? Well, first of all, every sound has its own intensity. That intensity is first of all compared to the threshold of hearing. So there's a comparison. It's what we call relative intensity. The intensity of some sound in ratio to what we're going to say is I sub naught, I sub 0, meaning the lowest one, right? The lowest of all possible sounds. So we're going to take this ratio, intensity of a sound, for instance, whatever volume, whatever intensity I'm speaking at now, which is, I'm going to guess, somewhere around the 1e-6 watt per square meter. It's probably about the intensity I'm making right now. We're going to compare that intensity to the threshold of hearing. This is what's called relative intensity. And we're going to take the logarithm of the relative intensity. That gives us the bells. But we want decibels. Well, if you have 8 bells, or in this case, 6 bells, how many decibels would that be? 60, because it takes 10 decibels to make a single bell, so 6 bells would be 60 decibels. So we're going to multiply 10 times this logarithm, and that's our formula for loudness measured in decibels. Beta equals 10 times the log of I over I sub naught. Now, naught, by the way, there's 3 spellings for naught, right? They're homonyms. K-N-O-T means like tying a knot. N-O-T means not him, or not her, or not that, whatever you're talking about. And then N-A-U-G-H-T means nothing, okay? 0, I sub naught. It's this knot, okay? Just in case you were wondering, how do I get the knot? It's not K-N-O-T or N-O-T, or there isn't that the Winnie the Pooh piglet. Can you tie a knot? I cannot knot. Those you can knot. No, I cannot. Anyway, okay, when you have small children, you think of those things. All right, anyway. All right, so say the formula with me, class. Beta equals 10 times the log of I over I sub naught. Again, we could refer to this ratio, class, as relative intensity. You're relating the intensity of a sound to the baseline, the lowest possible sound. All right, let's take a look, if you would, at page 262. By the way, you see a chart back. Let's start on page 261 because I didn't actually point this out. Page 261, we have the various intensities, right? And then you have the various bells and the various decibels and kind of the progression there as you go up. All right. Page 262 then. You have the equation there for decibels for loudness at the top of the page. Page 262, example 17.5. Read that for us if you would, Audrey.
What is the decibel rating of a sound with an intensity of 4.8 -5 watts per square meters?
Good, watts per square meter or watts per meter squared. So they give us the intensity and they want to know the loudness or the decibel rating. Well, as you see, it's in your calculator. Start by plugging in the 4.8 e-5. Class, we're going to compare that intensity to what? The I sub naught, the threshold of hearing, which is, class?
1.
So divide by 1e-12. And you get a really big number on your calculator, don't you? But we're going to take the logarithm of that number. So hit the log button, and suddenly it changes things up quite a bit, doesn't it? Then what you see on your calculator is the bell rating. We didn't multiply by 10 or just move the decimal back one place and we get the decibels. Did you get what the book had here? 76.81 blah blah blah, or rounded 77 decibels. Any questions on how to use the formula to find loudness? Seem pretty easy? All right, turn over to page 265 then. Page 265. And look at number 11. At your seats, do number 11. If we have an intensity of 3.2 E negative 3 watts per square meter, what is the loudness of that sound? It's pretty loud. And then what'd you get?
95.0.
I did not get that. Anyone else get 95? You did. Let me re-enter it on my calculator. I really ought to have my answer key here. 3.2 E negative 3 divided by 1 E negative 12. Take the log. That's not what I saw a minute ago. Take the log times 100. Yep, it is 95.05 blah blah blah. We'll round it to 2 sig figs.
95.
95
decibels.
decibels. There we go. 95 decibels. How many had 95 decibels? All right, so we all ended up with that, and I eventually got there on mine. Number 12. It says if one sound is 30 decibels louder than another, how many more times intense is the first? All right, well, flip back, if you would, to that chart on page 261, just kind of practically thinking this through. Pick a random decibel level to start at. Anyone? The 30 decibels?
Yeah.
All right, now go up 30 more decibels. Where are you at now? 60 decibels, okay? What is the intensity level at 30 decibels? 30? I got 10 to the negative 9th. What about 60? 10 to the negative 6. Notice a 30 decibel difference is an E3 difference. Do you see that? The E value went from negative 9 up to negative 6. That's an E3 difference. So a rise in 30 decibels is going to be a rise in how much intensity? E3 means 1,000. 30 decibels louder is 1,000 times more intense. Does that make sense? All right, and that's, again, you could technically do it mathematically there, but it's a little easier seeing the chart. Number 13 is interesting. Read this one for us, Michael.
If the sound at 80 decibels is hitting a 0.3 meter squared pane of glass, how much power is delivered to the glass?
What equation talks about power and sound, Michael?
I equals P over A.
I equals P over A, but it's asking us to find the power, correct? So if we need power, class, P is going to equal I times A. Now again, this isn't rotational inertia. We're using I for intensity again, but rotational inertia, sound, they have really nothing in common. So reusing the letter hopefully isn't too big of a deal. The problem is they don't give me the intensity, do they? What do they give me? They give me the
Decibels.
loudness, the decibels. What we need to do now is work through how to find intensity if I know loudness. I want you to watch the rearranging here. If I want to know intensity and I know the loudness, I have to get the I by itself. First thing we have to do is divide away the 10. Does that make sense? So we're going to take beta divided by 10. That goes from decibels back to bells. Then we have to get rid of the log. Remember what the log is? It says, what power of 10 is this? The opposite of the log is called the anti-log, and it basically says raise 10 to that power. Now, if you look at your calculator, look above the log button. Do you see that the anti-log right above it is 10 to the x? You're just going to do second function log, anti-log. But what you're doing is saying 10 to that power. And then finally, so that got rid of the 10. This gets rid of the log, the anti-log. How do I get rid of the I, or I sub naught? Multiply that by I sub naught. So it said we have 80 decibels, correct? So do this with me on your calculator. We've got 80 decibels, divide that by 10, which you could have done that in your head, of course, I know, to get 8. Now take the anti-log, second function log of 8. What you have in your calculator now is 10 to the 8th, which is 10 million? 100 million? 100 million, right? Now that value gets multiplied by the threshold of hearing. So multiply that times 1e negative 12. And what is the intensity here? 0.001. 0.0001 watts per square meter. 1/10,000th watts per square meter. Do we see how to put the equation in reverse? It's set up for you to know the intensity and find decibels, but we can get the intensity from the decibels if we divide by 10, take the anti-log, multiply by I sub naught. Coming back to this problem, we had 80 decibels, which we now know is 0.0001 watts per square meter. That loudness, that now intensity, hits a pane of glass that was what again, Michael?
0.3 meters squared.
0.3 square meters. Well, notice the per square meter and the square meters cancel to get how much power? 0.00003. So we're now up to 4 zeros, or we could say 3e negative 5, and notice power is simply measured in watts. 3e negative 5 watts, or they got two sig figs, so I guess I'd say 3.0, or 0.000030 watts. Either answer would be acceptable. Questions on this problem? The bigger thing to derive is how to get the intensity from the loudness. Does that make sense? Because here in a minute we're going to work problems that involve going both ways. All right? Look at page 262 now, if you would, please. Back to page 262. Read example 17.6 for us, if you would, Kendall.
A 3-foot in front of a stereo system. The loudness is 40 decibels. Calculate the loudness at 15 feet.
All right, so you're 3 feet away from the stereo system, and it sounds 40 decibels. What if you were 15 feet away? So, by the way, you kind of see that table on page 262. Interrupt there real quick. I'm still have the ADD here, apparently. So look at the different intensities, right? And so a soft whisper like this. Okay, I don't even know if the camera can still hear me or not, but 20 decibels. Normal talking, indoor conversation, not what the junior hires are doing, but normal conversation, right? Loud conversation, be a little bit higher up there, right? But you just see some different examples of what these intensities may sound like for your own benefit. Growing up, I liked listening to football games. We didn't have a television growing up. I had a radio, so I listened to the radio to listen to the football games, but the rest of the family didn't want to hear the football games. So I would turn on the radio and I would lay in front of the speaker. And so this, I'm kind of picturing me here, laying in front of the speaker on the floor, because I wasn't allowed to sit in Dad's recliner, which was next to the speaker. So I'd lay on the floor next to the speaker and I'd be listening. I'm about 3 feet away from the speaker, for instance. I've got the speaker turned down where I can hear it, but the rest of the family isn't bothered on Sunday afternoon. I want to listen to NFL football. They don't want to listen to NFL football. What if you were on the other side of the room? You walk into the room, how loud would it sound to you? See, that's what it's asking? Here's the problem. Distance from the source is related to intensity, not loudness. And you can't just plug loudness in because it's not the same thing. One's logarithmic, one's linear. So we know the first distance here, class, is 3 feet away, which gets squared. We know the second distance is 15 feet away. That also gets squared. But I can't find the loudness at 15 feet. I can only find the intensity. And I can't plug in the loudness at 3 feet. I have to plug in the intensity. So what are we going to have to do? Well, we're going to have to take the 40 decibels, and we're going to have to figure out what that intensity is, aren't we? So, with your calculator, let's get the intensity. First of all, when you plug in the decibels, you type 40. First thing you do, class? Divide away the 10. Then? Anti-log. Second function, log. Then? Multiply by the 1e negative 12. And I'm going to go ahead and put that into scientific notation because I don't want to write all those zeros. That's the whole point of scientific notation. What is the intensity of 40 decibels? 1e negative 8 watts per square meter. Now that I have an intensity here, now I can find this intensity. So we take the intensity I just found times 3 squared, which of course is 9. Divide by 15 squared, which do we remember? 225, good. And we get what intensity 15 feet away? 40 negative 10 watts per square meter. That's the intensity that a person walking in the room hears. But that's not with the loudness that they hear, correct? They don't actually hear intensity, they hear loudness. So, now guess what I get to do with that? I get to plug it in right here for the intensity to get the loudness. So what do I do with my 40 negative 10 class?
Divide it by, Yeah.
1e negative 12. Divide by I sub naught, which is 1e negative 12. Then take the log. Then multiply by 10. Now, if you're still in scientific notation mode, you're going to have an E1 on your calculator. That just means move the decimal back one place, or second function flow, and you have to get the regular one. What is the loudness 15 feet away?
26.02.
At 26.02, basically 26 decibels. So 3 feet away, it's 40 decibels. 15 feet away, it's 26 decibels. The intensity drops dramatically. Loudness doesn't drop as dramatically because loudness is not dramatic. Intensity is. Loudness is logarithmic. Questions on this example? You kind of see how you've got to be able to work both ways with the equation. All right, the nice thing is it's pretty straightforward. You multiply or divide, take the log, multiply by 10. Or divide the 10, take the anti-log, multiply the 1e negative 12. Turn over to page 265. Turn over to page 265 and read problem 14, if you would please. Audrey.
The noise from a racing car motor is 80 decibels at a distance of 10 feet. What is the loudness at 2e2 feet?
All right, 2e2,
Yes.
so 200.
Yes.
All right, and the first distance was what again? 10 feet away?
Yes.
All right, now, I know my dad went to Indy, the Brickyard, for the time trials and stuff. I'm pretty sure it's louder than 80 decibels if you're within 10 feet of the car. But maybe the engine's just idling. Maybe it's in pit road or something where it's not super, super loud. But it says at 10 feet away, you're hearing 80 decibels. All right, so you're right there near the pits. At 200 feet, okay, so you're up in the stands a good way back. Now, how loud is it? What equation relates distance and sound? Class? Good. But it's not loudness and distance that are related, class. It is intensity and distance. So while the distances are clearly spelled out, 10 feet, which needs to be squared, and 200 feet, that needs to be squared, the intensities aren't spelled out. So what do I need to do first? Convert it into intensity. At your seats, convert 80 decibels to intensity. Call it when you've got it. Gravity still works. I was curious about that. No, okay, good now. Just clumsy. Divide the 10, take the anti-log, multiply by 1e negative 12. Go ahead, Kendall. 0.0001 watts per square meter. So we get the same thing. Or maybe if you were in scientific notation, 1e negative 4. Now that we know the intensity, I can find the intensity up at 200 feet away. Again, that's not what the person's going to hear, but we can find the intensity that hits them. When you have the 200 foot away intensity, call it out. 2.5 e negative 7 watts per square meter. Did we get the same thing? Or like 0.6025. All right, now that's the intensity, but they don't hear intensity. They hear loudness. That's the way the human ear perceives intensity. So at your seats, make that loudness. Again, divide the 1e negative 12, take the log, multiply by 10, call it when you got it. 53.97, blah, blah, blah. Pretty much, I believe it's 2 sig figs again, right? Yeah. So 54 decibels. 80 decibels up close, 54 decibels further back. All right, questions on this equation? You're going to practice a little bit with that in your homework this evening. Next thing in your notes, what you read about last night in your homework reading, pitch. Pitch. Oh, actually, no, I do have a fan in here. Perfect. It's a really simple illustration. I don't have that crazy Smartsville thing that they talk about, but I do have a fan. And what I want you to do, and I'm not sure how well the audio will be picked up on the camera, but at least those in the classroom should be able to hear this pretty easily. Okay, when I turn on the fan, I just want you to listen. hear the hum. Now it's a little louder as well. Apparently this generated an air current that started drawing air, and one of the test tubes started rolling and almost shattered. All right. Do you notice how it not only got louder, but also went from the I'm checking over there. Okay. So we hear as the fan blades spin faster, right? What they're doing is they're hitting the air more quickly. They're causing a faster series of compressions and rarefactions to go. Faster meaning more per second, meaning higher frequency. But what we hear, and I've alluded to this already in talking about the Doppler effect, is it sounds like the pitch goes higher. That's your definition, if you will, for pitch, is the way the human ear perceives frequencies. Or specifically, the way the human ear perceives audible frequencies. Not all frequencies of sound can be heard by the human ear. And we're familiar with this already, right? We know that some animals hear sounds we don't hear, such as dogs, a good example. Dolphins, a good example. Is that what you said?
I said dog whistle. Dog
whistle, yeah, the dog whistle, of course, is used to really high frequencies. Horses, I believe whales can hear sounds that lower than what we can hear. So there are other animals whose ears are designed to hear frequencies we don't hear. We have a set range of frequencies, but within that range of frequencies, the frequencies we hear are called, we classify those frequencies the way we hear it as pitch. Pitch. We know that the audible spectrum, spectrum simply referring to a range of values, okay? So a range of values that we can hear. The audible spectrum runs from 20 hertz to 20,000 hertz. Now that's for a healthy human ear. Okay, that does not mean that every human can hear frequencies as low as 20 hertz and as high as 20,000 hertz. Now admittedly, most humans, they never lose the low end. Most people can continue to hear frequencies on the low end. But on the upper end, those higher frequencies, as you get older, as your eardrum, through years and years of compressions and rarefactions, begins to lose a little elasticity, you can't detect the higher frequencies as well. And so that number comes down as you age, or if there's some sort of trauma that happens. This is one reason why when you're talking with grandparents, they can't always hear too well. And what's our natural response when somebody can't hear us? Hey, Grandpa, how you feeling? Hey, what, Shelly? How you feeling, Grandpa? I still can't hear you. Grandpa! Well, I got louder, but what happened also? My pitch went up, my frequency went up. Is that helping Grandpa? No. This is also why sometimes, hey, Kendall, did you hear about Grandpa? What are you saying about me? Right? Well, why is that? Well, because when you whisper, your voice tends to go lower. Not only is your volume decreasing, but a lot of times your frequency does as well. And so it's like, I was just screaming at that man, he couldn't hear me. Now I'm whispering, he hears me. I think Grandpa's faking. Okay? Well, that's not actually it. It could just be that when you're speaking, you're talking lower. So one of the things I tell Chloe, because my father-in-law's hard of hearing, to Chloe, you've got this sweet, beautiful voice. Grandpa can't hear that. You've got to talk louder and lower. Talk louder and lower to Grandpa so he can hear you. Oh, okay. Hey, Grandpa. It's okay. She's 8. She'll learn. But anyway, that's simply because we begin to lose that upper end of our hearing. This is one reason why, I think there was something going on in English class one time. Mrs. Henderson was griping about it. She's like, there's this sound that the kids can hear that I can't hear. I don't like that. I'm thinking to myself, well, I don't know what to tell you. I'm not going to tell you, But it's just the way it is in life, okay? There are certain frequencies that you just don't hear as well as you get older. So again, this range here doesn't mean everybody hears that. That's for a healthy human ear. Anything up here above the 20,000 hertz, are those sound waves that have frequencies that high are called ultrasonic waves. Ultra meaning above or beyond, sonic referring to sound, not hedgehog. Okay, ultrasonic. It refers to frequencies beyond or above what the human ear can hear. There are also sound waves that have frequencies lower than 20 hertz. These are referred to as infrasonic waves. Infrasonic waves. Ultrasonic waves particularly have some very interesting uses. The book references a couple of them. One of them is they actually talk about trying to break up kidney stones with ultrasonic waves, really high frequency sound waves. So nobody's hearing these, right? These waves are being emitted. Nobody hears them, but they have enough energy because remember, as you increase the frequency, that increases intensity, right? One of the factors affecting intensity. And so it can break up kidney stones to allow them to pass less painfully. I am all for anything that makes things less painful in life. Never had one, but I've heard horror stories. So I'm like, it's good to know there's something out there that can help if they'll use it. Usually they just tell you to pass it and it's just painful and awful. But perhaps the more common example of ultrasonic, ultrasound, of course, we think of imaging, especially babies, right? My wife's had 4 kids. And so it's been interesting with each one of them to see the ultrasound. But basically they just shoot those high frequency waves into the womb, and as the waves bounce or reflect off, there's an imaging, kind of like sonar for babies. Or they do it for other things. It's not just babies, but as a sonar, it bounces off. You can see based on the reflections what the receiver's set up to pick up is, oh, this is what the head looks like. This is where his hand is. This is what the baby's gender is. That's always the fun one, right? And unless you don't do that. And there are some people who they like to be surprised. And I don't do well with surprises. So it's like, no, I just need to know what I'm having. This is going to be a boy or a girl. Let's plan. I can't plan if I don't know, and I have to plan. But anyway, ultrasound. It uses ultrasonic waves. Are they dangerous? No, they're just sound waves. They're just high frequencies you can't hear. Another thing with music, and we referenced this already in the homework time, but with music, notes that are 1 octave apart are a doubled frequency. So octave notes are doubled or halved frequencies between them. Let's just say, for instance, that we take a starting note at, let's just say, 240 hertz. What would be 1 octave higher than 240 hertz, class? I said if you go up an octave, you do what to the frequency? You double it, right? That's why it sounds the way it does, because it's a pure doubled octave, pure doubled frequency. So it would be 1 octave higher than 240 hertz. 480 hertz. All right, what would be the next octave higher? 960 hertz. If you went another octave, you're up to, I was getting 1,920.
Yeah.
1,920 hertz, you multiply by 2. All right, what if you went down an octave from 240 hertz? 120 hertz. What if you went down another octave? And you're rapidly approaching, by the way, the low end of your audible spectrum, aren't you? And so that's just how the octave works. Just go doubling to go up, or halving, H-A-L-F-I-N-G, to go down. All right? Questions on the octave. Questions at all on pitch. Again, with all this talk of frequency with the Doppler effect, pitch is what we are hearing. Now, word of caution. Every year, quizzes, tests, students don't read questions. The way the human ear perceives, there's 2 different things I could put there. Intensity or frequency. The way the human ear perceives intensity, class, is loudness. The way the human ear perceives frequency is pitch. All right? So we've got to make sure we keep the 2 straight. Okay, so 2 different terms I taught today. Both of them refer to the way the human ear picks things up. Intensities, loudness. That's the one that's a linear to logarithmic relationship. And then frequencies we hear as pitch. All right, questions at all on pitch? All right, that pretty much wraps up chapter 17. We'll be reviewing over chapter 17 in our next lesson. And then moving on to chapter 18, which is where we'll transition from all this talk about sound to talking about light. But anyway, for homework this evening, go ahead and reread over pages 263 to 264. Reread over pages 263 to 264. Wouldn't hurt to go and study over all of chapter 17, but focus specifically on those pages. Page 265, just 2 problems for you to do. Problems 15 and 16. Page 265, problems 15 and 16. All right, have a wonderful rest of your day. When the bell rings, you'll be dismissed.